So in this section, we're going to dive deeper into numerical integration. We've already kind of introduced ourselves and got our feet wet with previous sections where we talked about the left-hand rule, the right-hand rule, and midpoint rule. So in this video, we're kind of just going to glide over that. But the fundamental theorem of calculus gives us a direct way to calculate the exact value of definite integrals. All right, so fundamental theorem of calculus tells us if I have some integral from a to b f of x dx, I can get some exact value. Maybe the answer is like pi. Now, this only works if I can actually find what the antiderivative of little f of x is, meaning I have to find the antiderivative, evaluate it at b, and then subtract it from the antiderivative evaluated at the lower limit a. Now, unfortunately, in the real world, finding antiderivatives is really, really difficult. So most times it's impossible to do, especially given the fact that we can't even fit some of these functions into an elementary form, meaning like I can say f of x is like x squared plus 2x, like that's an elementary function, or f of x equals sine of x squared, right? So because this is the case, we can find derivatives of any function, all right? So no matter how complicated the function is, I can find the derivative of a function. Like this one right here, there's no way, I don't have the tools right now to find the integral of sine of x squared, but by golly, I can take the derivative of sine of some stuff. Derivative sine of some stuff is cosine of the stuff times d dx the stuff. And so that would just be cosine of x squared times 2x. No big deal, right? But integrating sine x squared is a little bit more challenging, to say the least, okay? So there are not many functions out there that actually do have closed form antiderivatives, right? So we can find the derivatives of any functions, but there are many functions that the closed form does not exist. And if you want to learn more about how to calculate integrals of like sine of x squared, you're going to need to take Calculus 2, and the capstone of that class, I'll show you how to actually calculate those things using infinite series, which is pretty awesome. Very much encourage you to take Calculus 2. It really is a great class. Even if you don't need it, it will make you a better student, I promise you. Okay, so integral from some amount, if I want to find the indefinite integral of e to the negative x squared, why is this function important? Well, this function is very important in statistics. If you've ever heard of the normal curve, I know it's been beaten to death, but you've heard this thing called flatten the curve, right? So that curve that they're referencing is that normal curve, all right? It's very huge in probability and statistics. And the graph of y equals e to the negative x squared happens to be how that normal curve is defined. The only thing different is it's got this constant 1 over square root 2 pi out in front to make it to where the area under the curve is equal to 1, because that has something to do with probability. Can't have a probability greater than 1 and area is equal to probability. Okay, so this is a very important integral, because in order to find the probability using a normal curve, we've got to be able to somehow figure out some closed form or some approximation to this. So this is where numerical integration comes into play and is like super applicable in today's society. Okay, so where we let the computer do the work for us. So so far we've learned how to approximate definite integrals. We've got the left-hand rule, which says that like we use left-hand endpoints. Okay, so to approximate the area under curve from A to B, so we're going to do from like 0 to 3. of this curve. So we're on the right side of the normal curve. So remember I had drawn that normal curve like this. So we're just doing from here to here. Okay, so 0 to 3, we're trying to approximate that area under the normal curve. Okay? And so left-hand endpoints, whenever I draw my rectangle, the left-hand side is the point that touches the curve. Okay, and then I figure out what that is equal to. Well, to do this, I use a sum from k equal 1 to n of f of k. So that first value input, second value input, third value input. And I get my f values there. The height of the rectangle times the delta x, the width, gets you the area of each rectangle. And so the next one, the right-hand rule, instead of starting with x1, we start with x2. We plug in x2, we get this f of x2. Plug in x3, get f of x3. Plug in x4, get f of x4. So instead of starting with k, I'm going to start with k plus 1 so that I can skip that first one. So that's literally the only thing changing from here to here is I use a k plus 1 for the right-handed rule. Okay, the midpoint rule is exactly how it sounds. Instead of going on the left side or the right side, I figure out the average, the midpoint between the two. How do I get the midpoint? I add the left-hand point, the right-hand point, and then divide by 2 to get that middle point right there, and then I plug those middles in just like that. So the midpoint rule out of those three is probably the best rule. It's a little bit more complicated. If the function is a decreasing function on the interval that you're approximating, then the left-hand rule is an overestimate. The right-hand rule is an underestimate. The midpoint rule is somewhere in between depending on how steep it is. Okay, so and then go in the other way just to make a point. If the function is increasing, the left-hand rule would actually be an under approximation, and the right-hand rule would now be your over approximation. Okay, so depending on if the function is increasing or decreasing, that's either going to be the upper or lower bound of what that sum would be. Okay. And if you go far enough into advanced calculus, those sums, those limit supremums and limit infimums, those will become more and more important with that upper and lower bounds. Okay, kind of like the squeeze theorem when we talked about the first of class, where sine of x was stuck between -1 and 1, and we use that to our advantage to figure out limits. So n here represents the number of rectangles. For each of these problems, we had n equal to 3, okay? So n equal to 3 rectangles for each of those. And our delta x, we took the interval that was from a to b, so we did b minus a, and then we divided by n there. So a and b are my limits of integration. So if I was integrating from a to b, of e to the negative x squared dx right there. Okay? So what I want to do is I want to take my graph and I want to integrate from 0 to 3. Okay? Now, I think that I can do this on a calculator. Maybe this one might not. But there is a way, I believe, that you can type this in. Let's see if we can do it. I may not be able to do it. So I just went down to math and then down to the integral. So let me clear this out and do that again. So go to math and go down to 9 where fn int. Okay, and then hopefully yours is in this version. If it's not, yours is going to be a little bit more complicated, but it is doable. And you can Google how, what the parentheses are to type that in. I think it's like you type in the function and then you put a comma, and then you put the variable that you're integrating with respect to, then you put a comma, then you put your lower limit, so like from 0 and then comma, and then your upper limit 3 and then close the parentheses. I think that's what it is, but it might be different. So just you can look it up, TI-84, how to integrate math fn int. Okay, and then If you Google that, I'm sure it will pop up right away. So I'm integrating from 0 to 3 of e raised to the negative x squared, enter, and I get 0.886207. So that's there for your benefit. So now I want to introduce an even better rule here. This is the trapezoid rule. So what the trapezoid rule does is it, instead of adding rectangles, we are now going to add trapezoids. Now, why is that beneficial to us? Well, if the angle is sloping, like that slope there could be very much incorporated to give us an even better approximation than the midpoint rule does. So I need to remind us, how we find the area of a trapezoid. So I have a height here in a trapezoid, and I also have a height here. So I have two heights, and really what's happening here is I'm taking my trapezoid, okay, and I'm going to cut this piece off, and I'm going to take that piece and I'm going to put it over here. And if I put it over there, now what type of shape do I have? Well, I'm back to a rectangle, right? So the question is, what's the value that I need to plug in here that's going to cut it straight in half so that I have exactly that? And you guessed it, this value is the midpoint, okay? It's the average, right? It's the average of the H1 and H2. So it's halfway in between both of those. So I'm going to average H1 and H2 to get my height, and then I'm going to multiply by my base. Okay? So what is this equal to in terms of my function? Well, I plug in a height, which is like an f value, and then I plug in the next f value. So f of x1, and then f of x2, and I divide by 2. And then my width here is just like my width was here. It's just another delta x. Okay? So this is the way it works for the trapezoid rule. So I want to do trapezoid rule for n equal to 3 here for this problem. And so if n equals 3, I need 4 x values to cut it up into 3 equally partitioned delta x's. So the first trapezoid, look at how I drew the trapezoid. Look at that. There is barely any area that wasn't counted. See how much better that is versus that first trapezoid? Look at all that area that was counted or failed to count, and then all that extra area that was counted there. I mean, don't even get me started on how much area was missed with the right-hand rule and then over area on the left-hand rule, right? So the trapezoid rule really works well for slope curves here. You can see how minimal the error is going to be. Okay, so I'm going to do my 3 trapezoids. Look at that. It almost looks like it's exactly like the curve is. It's only slightly off. So it really doesn't take many trapezoids for us to get a great approximation. So it's very useful. Okay, the quicker you can make the algorithm calculate your area for you, like this your calculator literally uses an algorithm to get this answer here. Okay, it uses a numerical methods algorithm that calculates it for you so quickly. So the quicker you can do it, the faster your calculator works. So I have f of x1 plus f of x2. So I'm trying to get that average height. So I divide by 2, and then I multiply by my delta x. So that's the first area of a trapezoid. The next one, I do f of x2 plus f of x3. So that's this one right here, divide by 2. So that's that second trapezoid. And then the last trapezoid, f of x3, f of x4, divide by 2 to get the average, and I get that. So those are my 3. I'm going to use blue here because I've shaded in blue. So 1, 2, 3 trapezoids. Now all I have to do is plug that in and add it up. Okay, so what do I notice? each of these terms here has a delta x divided by 2, delta x divided by 2, and delta x divided by 2, right? So I'm going to factor that out of each of those. So I've got 3 terms in here, and I pulled the delta x divided by 2 out of each. So the first one, so now all I have left for each of them is this. So I have f of x1 right here, okay? And then I have f of x2, but what do you notice? There's an f of x2 here and an f of x2 here. So I've got double of those, so I'm going to put 2 there. And then I have f of x3, but I also have another f of x3 here. So I'm going to double that up too, okay? And then I have 1 f of x4 here. So you notice what happened. There was only one fx1 and one fx4, but you had an fx2 and an fx2 here, and then you had an fx3 and an fx3 there. So you doubled up here, and you doubled up here. So it ends up being the case, and I'll talk about this a little more at the end, but it ends up being the case that all the terms in the middle are going to be doubled. The only one that there's only a single is the very first one and the very last one. So the f of A only has 1 and the f of B only has 1. Okay? All right. So simplify here. Delta x, well, how do I calculate delta x? Delta x, and then I plug in f of, well, what is my function? My function is f of x equals e to the negative x squared, right? So e to the negative something squared for each of those values. So I need to figure out what x1 is, x2 is, x3 is, x4 is. And once I do that, then I will be able to just plug in. Okay? And so how do I do this? Well, x1, what is x1 equal to? From my picture, it looks like x1 is equal to 0. x2 looks like that's going to be a 1. x3, see, once I get these values like x1, I plug in here, right? x2, 1, I plug in here, okay? x3 is 2, and I'm going to plug that in here. And I'm just going to keep running through with this. And x4, which is this last one here, okay, I'm going to plug in a 3 for that right there. Okay, so that was pretty easy. This is 0, 1, 2, and 3, since I'm integrating the interval from 0 to 3. Okay, so I literally plugged in these values for these functions into e to the negative x squared. Now, what else do I need? I need delta x. How do I get delta x? The formula for delta x is b minus a over n. b minus a is 3 minus 0 over 3, which is just 1. So I'm going to replace delta x with 1 there. And then I'm going to do the math. And so you type this into your calculator. I know it's kind of cumbersome to do, but it is definitely doable. So, I mean, I guess I could simplify this like 1/2, and then this is going to be, I guess, 0. E to the 0 is just 1 plus 2 times e to the negative 1 plus 2 times e to the negative 4 plus e to the negative 9, okay? So that just, you know, whatever the heck that number is, right? So that means nothing. So let's type that in the calculator, and it outputs 0.886257. Holy smokes. Why is that cool? Because 8862, okay, those are the first 4 digits of what the calculator said. So once we get out to 5 digits, we start seeing some difference in what the values are. And so that's really not bad to do 3 trapezoids and to be within 10 hundredths, thousandths, 10 thousandths. We're correct to 10 thousandths of a decimal. That's pretty awesome if you think about it. Okay, so trapezoid rule, truly powerful. And here's the rule written out in general. It's b minus a divided by 2n. Okay, so that's the big difference, divided by 2n. And then I sum the first rectangle, or the first height, f of a, which is f of x1, that first one here. And I sum the last one. But everything in the middle, like I said, everything in the middle here gets counted double, okay? It's only the very first one and the very last one that only get counted one time. And it's because you see that you've got this overlap situation going on. Just like this overlap situation going on. This F2, F of 2 gets used for that trapezoid, but it also gets used for this trapezoid here. And then same with this F3 gets used for trapezoid number 2 and trapezoid number 3. So any of the ones that find themselves in the middle, all you've got to do is just multiply by 2. Okay? It's only the n values, the ny values that are f of x1, and then the last one f of xn plus 1.